This is lesson 3.3a. In lesson 3.3a, we're going to start talking about linear functions. And a linear function is a function whose graph is non-vertical. So that means it cannot be going straight up and down like this. It has a constant rate of change, meaning it goes up or down by the same amount every time. And can be represented by a linear equation in two variables. And for a linear function, our equation that we use is y equals mx plus b. So as I look at these graphs here, right, I notice that this graph has a curve to it. Since this graph has a curve to it, it cannot be going in a straight line. It is not increasing by the same amount every time or decreasing by the same amount every time. If I look over here, that section is decreasing while this section is increasing. So it's not doing the same thing every time. Therefore, this one would be non-linear. For B, if I look at it, first off, a really good indication is that it's just a straight line, but not vertical. And the next thing that I can look at is as I move over one line here, I'm moving up 1, 2 lines here. So if I move over one more line, I'm moving up 1, 2 lines here. So this does seem to be going up by the same amount every time. I can even check down this way. Over 1, up 2, over 1, up 2, over 1, up 2, over 1. So I continue to get back onto that line. So it is a straight line. It is going up by the same amount every time. This one is linear. For C, again, it does look, as I go left to right, it does look like it's consistently increasing, but not by the same amount. And this curve on the side here is a really good indication to us that it's not linear because it's not forming that straight line. And the constant rate of change is what makes it form that straight line. So this one is also non-linear. So that's how we can find it from a graph. Let's also take a look at a table. So whenever I want to know if a table is showing me a constant rate of change, because I don't have the graph to look at, I have to look at how the y values are changing over how the x values are changing. So for example, if I look at these y values here, from 36 to 30, we went down 6. 30 to 24, down 6. 24 to 18, down 6. Now I also have to look at the top of x values. From 3 to 6, 3 to 6 is up 3. 6 to 9 is up 3. 9 to 12 is up 3. So the way that I determine whether this truly is linear or not, I have to make fractions out of each of these changes. Okay, and I'm always going to do y over x, y over x, y over x. So I'm going to write that down on my paper here. So this is example 2. Letter A, I have negative 6 over 3. For my second one, I have negative 6 over 3. And my third one, I have negative 6 over 3. So this one is a little bit easier to kind of recognize because all of these fractions started out with the same things, right? So negative 6 divided by 3 equals negative 2. So if these fractions simplify to the exact same number, that means we do have a constant rate of change. That constant rate in this case is negative 2. And therefore, this is a linear relationship right here. Now we're going to check out the second example in this one. So part B, let's look at our y values here. So from 2 to 9, we're going up 7. From 9 to 20, we're going up 11. And from 20 to 35, we're going up 15. So at first glance, looks like they might not be. However, remember, it's not about just how these are changing or how these topos are changing. It's about the fractions that we make simplifying to the same things. So from 1 to 3.5, we went up 2.5. From 3.5 to 6, we went up 2.5. From 6 to 8.5, we went up 2.5. So if we make our fractions, so we got part B here. We had 7 over 2.5. We have 11 over 2.5. And we have 15 over 2.5. So this one, again, we have the same denominator. So it's easier for us to compare. Are 7 2.5 over and 11 over 2.5 and 15 over 2.5, are they the same fraction? Can they reduce to the same thing? Absolutely not. So because they cannot, then we would say that this one is non-linear. It's not going up by a constant rate. So when we look at a graph, we're looking for a straight line, moving up or down at the same rate every time. When we're looking at a table, we have to find the change in the y over the change in the x, make sure they simplify to the same fraction. And we're also going to take a look at the equation. So if you haven't yet, pause your video and cut out the equations that are at the bottom of your notes sheet. Welcome back. So up at the top here, we have our example for the linear equations. And what I want you to know is that constant rate is this letter M here. So that constant rate we've been talking about. And then eventually we're going to get talking about the letter B, but I just want to label it as green because that's what I always use for that one moving forward. All right, so let's look at example 3. Trying to determine based on the equation whether or not this is a linear equation. So I'll rewrite her. Y equals mx plus b. All right, so the first one I'm going to take a look at here is x squared minus y equals 0. Well, the first thing I notice is it does not start y equals. So if I want to quickly determine whether or not this is a linear equation or not, I need this equation to be starting with y equals, if possible. So let's take a look. For example 3, we're going to use that equation we just selected here. And we're going to rewrite it. So those literal equations we did in the past, when we had to solve for certain variables, that's going to help us out here. So if I want to get y by itself, the first thing I would do is add y, since this is minus y. So that's going to leave us with x squared, equals y. I like the way that it looked before with the y equals. So I'm going to rewrite, just kind of flip everything, y equals x squared. So this equation here can be rewritten as y equals x squared. And if I compare y equals x squared to y equals mx plus b, notice this x does not have an exponent on it. Because it does not have an exponent on it, we have to decide that this equation here would be nonlinear. All right, next one we're going to choose y equals 6 times the quantity of x minus 1. So it does start out y equals. However, I don't see parentheses in here or anything, and I know that I could simplify this one a little bit. So I'm going to take that to my notes over here as well. So it was y equals 6 times the quantity of x minus 1. So again, just like when we solved our equations, we're going to distribute our 6 here. So I have y equals 6 times x is 6x, 6 times negative 1 is negative 6. So if I compare that to y equals mx plus b, we got y equals, if we have a number attached to x, that's that constant rate of change we were just talking about. And then in the original it says plus b, but remember we could also rewrite this as 6x plus negative 6. It looks kind of weird, but we could do it that way. So don't be fooled. Just because it has a subtraction doesn't mean that it doesn't qualify. So even though it has a negative, it still qualifies. So that one would be a linear equation. All right, next one, y equals 2 over x. Well, does this show x as the bottom of our fraction? No, it does not. So therefore, it's nonlinear. This one starts out y equals 3 to the power of x. Just like we talked about with this one here, if you have x as an exponent or you have an exponent on your x, then it will not be a linear equation. Next one we're taking a look at is y equals 3.8. So this one looks a little bit tricky, and I want to show you something here on your paper. So we have y equals 3.8, but our original has y equals constant rate times x plus b. And what I want to show you is, what if my constant rate was 0? Like, what if it just went up by nothing every time? So if I had y equals 0 times x plus 3.8, 0 times x is 0. 0 plus 3.8 is 3.8, just like we had up at the top here. So this, even though it looks a little bit different, is still linear. So if you have y equals just a plain old number, then yes, it is a linear equation. And last but not least, y equals the square root of x. Just like with our exponents, there's no square root written in this example here. So if you have a square root written into your equation, we would have to say that it is non-linear. This is lesson 3.3b. In lesson 3.3b, we're going to be talking about discrete versus continuous data. So if we look at it, first of all, a solution to an equation in two variables is an ordered pair. So the x value stands for something and the y value stands for something, but together they form a dot, and the dot is the solution. Okay. Sometimes these dots are distinct, and other times we connect them together. So for example, if you're talking about discrete data is when each individual dot is a solution. So for example, if I go to the store, I cannot buy part of a can of paint. They're not going to let me. I can buy the whole can. I can buy multiple cans of paint, but I can't buy part of a can of paint. So I have to buy whole quantities in order to be able to actually purchase this from the store. For continuous data, continuous means that it's a whole set of things between these two dots here. So for example, if I go to the store and I buy produce, right? I pick up a bag of grapes. They don't charge me for a whole pound if I'm not buying a whole pound. So when I put it on the scale at the checkout counter, it measures the whole pounds, but also measures partial pounds. So they only charge me, if I have 1.5 pounds, I only have to pay for 1.5 pounds of grapes instead of 2 pounds of grapes. So continuous data shows us that those things could be connected. It's numbers that lie between those dots as well. So we're going to take a look at example 1. It says the linear function y equals 1.25x represents the cost, y in dollars, of x bottles of orange juice. Each customer can buy a maximum of 5 bottles. So we're going to find the domain of the function. We want to know if it's discrete or continuous, and then we're going to graph it using its domain. So what I have to look at first is, what is the domain? So it says I can buy maximum of 5 bottles. So that means I can't buy any more than 5. So my domain, for example 1, we have a maximum of 5 bottles. But here's my question. Can we buy part of a bottle of orange juice? No, we cannot. Even if you tried to drink part of it in the store, they're still going to scan the code and charge you for the whole bottle. So if we're looking at our domain, we could buy 0 bottles. We could buy 1 bottle. We could buy 2 bottles. We could buy 3 bottles. We could buy 4 bottles. Or we could buy 5 bottles. But I can't buy partial bottles. So we know, based on this information, that we are dealing with some discrete data or discrete domain. So in order to graph this, we need to have some points. So what I'm going to do is make a quick input-output table. So our input is our x, which we just decided our domain was 0 to 5. 1, 2, 3, 4, and 5. We've got our rule, which it says that each bottle costs $1.25. So 1.25x is our rule. And then we've got our output, which is that y value. And then we'll have our ordered pair when we take our input and our output together as a point. Okay, so we have 1.25 times 0. Well, if I don't buy any, I don't have to pay for anything. So I have a point 0, 0. If I buy 1 bottle, 1.25 times 1, then I pay $1.25. So I have the point 1, 1.25. So notice we're just taking our input and our output and making them an ordered pair. If I buy 2 bottles of juice, 1.25 times 2 is $2.50 or 2.5. So I have 2, 2.5. $1.25 times 3 bottles is $3.75. So I have the point 3, 3.75. 4 bottles of juice, 4 times 1.25 gives us $5. So we have the point 4, 5. And then $1.25 times 5 bottles of juice gives us 6.25, and the 0.5, 6.25. So if I were given these points, then I, in order to interpret them, have to know that the X value stands for the bottles of juice, and the Y value stands for the cost I'm paying for those bottles of juice. So if I buy 0 bottles, I pay $0. If I buy 1 bottle, I pay $1.25. 2 is $2.50. 4 is $5. 5 is $6.25. So however many you pay or you buy, that's that X value, and how much you pay for those bottles is your Y value. So we're going to plot these on our graph. So we have 0, 0, and then we have 1, 1.25, so over 1, up 1. We got to kind of estimate a little bit here. 2 and 2.50, so that's halfway between 2 and 3. 3 and 3.75, so that's almost a 4. 4, 5, that would be a nice one right there on the dot. And then 5 and 6.25, so just about $6 there. Now, because this is discrete data, we cannot have partial bottles purchased. We leave these as just plain old dots. We cannot connect them, because if we connect them, it means I can buy part of a bottle of juice and they'll only charge me part of the cost of that bottle. So no connecting, because they are not continuous data. For example 2, your friend runs at a pace of about 5 miles per hour. So we're going to explain why the number of miles ran is a function of the number of hours spent running. We're going to find the domain of the function and then determine whether this domain is discrete or continuous. And then we're going to graph the function using its domain, similar to what we did in example 1. So for that first part, we have to think about as the number of hours increases by 1, the number of miles increases by 5. Because notice he's running at 5 miles per hour. So as each hour increases by 1, the miles increase by 5, which means that the rate of change is constant. So he's keeping up this pace consistently, which means that this is a linear function. All right, so can he run for part of an hour? He absolutely could run for part of an hour. So because of that, we would say that this is continuous data. And we know that he can't run negative hours, right? Because time doesn't go negative. So for our domain, we would say that it's any h can be greater than or equal to 0. Because he could choose not to run at all, right? And then he would just have 0 miles run. But he also could choose to run for part of an hour if he wanted to. So our domain for this one, we would say h is greater than or equal to 0, because he could run 0 miles. And then we're going to use this continuous data, and we're going to make an input-output table. So our input that we're going for is the number of hours that are run. And I'm just going to choose the same numbers we used for our previous question. I can count here. There we go. And then our rule, he's running 5 miles every hour, so 5 times h. Our output is the distance, that total distance that he runs. And then we've got our ordered pair. So in this case, we have our hours followed by our distance. All right, so 5 times 0. If he decides not to run any hours at all, he's run 0 distance, so we've got the 0.00. If he runs for 1 hour, he's run 5 miles, so we've got the 0.15. If he runs for 2 hours, 5 times 2 is 10, so we have the 0.210. If he runs for 3 hours, he's run 15 miles, so we have the 0.315. 4, we've got 20. And 5, we have 25. So now we have to take these points and plot them on a graph. So since we talked about them being continuous data, we have 0, 0, 1, 5. Notice that the y column is being counted by 5 for each line. So just be careful of that when you're graphing. 2, 10, 3, 15, 4, and 20, 5, and 25. Now, because we decided that it is possible for him to run part of an hour, and we said it's continuous data, we are going to connect these dots with a line. This is lesson 3.3c. In lesson 3.3c, we're going to take a look at a couple graphs. And we look at example 1. It says, write a real life problem to fit the data shown in each graph. Is the domain of each function discrete or continuous? So as I look at this graph, the first thing that I notice right off the bat is that all the space in between these 2 points are connected with a line. So as a result, I know that this is continuous. Now I need to come up with a scenario that will match this circumstance. So if I'm looking at this, then I can see that maybe I'm biking, right? And I have been biking 60 miles, and it took me 6 hours to bike those 60 miles, right? So every hour, perhaps I was 60 miles from home, and every hour I got closer to my house. And then when I finally got there, the end result was 6 hours. So my scenario would be that I am going, if you look at it, each of these kind of goes down, like as I go down 10 miles, it took me an hour. So it looks like this person who's biking is getting 10 miles closer to home every hour that they're riding. Let's say that's our scenario. So X would stand for the number of hours, and Y would be the miles remaining. So as we're getting closer to home, perhaps. If I wanted to write an equation for this, then I would say that I started at 60 and I subtracted 10 times x to equal the miles remaining. For example 2, it says, write a real life problem to fit the data shown in each graph. Is the domain of each function discrete or continuous? So just like with example 1. So again, this time I'm noticing I have very distinct points, but they are not being connected. So because they are not being connected, I know that this is discrete data. And if I were to give this a scenario, then perhaps we have a person who's playing on a game show, right? And they're earning money, or looks like maybe in this case they might be losing money. And what we see here is X would be the number of questions answered incorrectly. And Y is the total money earned. So if I answer 0 questions incorrectly, I'm going to get $60. If I answer 6 questions incorrectly, I'm going to get $0. So each of these points on our graph can represent a scenario where number of questions we answered wrong and how much money we would have earned in that instance. You can come up with your own story to match these as well. So there could be different things, even with our continuous one, for example 1. There's other scenarios that we could have that would lead us to a similar graph. This is lesson 3.4. Lesson 3.4, we're going to be talking about function notation. So function notation is like we've been working with through most of this chapter, where you say things like f of x. And so in this one, we have f of x equals mx plus b. It really means exactly the same thing as when we had seen previously y equals mx plus b. They mean the same. They just replace y with that function notation, that f of x. And it really could be any letter. It could be f of x, g of x, h of x. I mean, really any letter in the front would be fine. It's just showing you that it's a function in this form. So if we're looking at example 1, it says evaluate f of x equals negative 4x plus 7 when x equals 2 and x equals negative 2. So what they're asking us to do in example 1, first off, let's copy down our equation here. So we have f of x equals negative 4x plus 7. So they want to know when x equals 2 and when x equals negative 2. So all they're asking you to do is replace the x with 2 and then replace it with negative 2. Now I want to show you something here. So if I'm checking the 2 first, for example, when I see this written as f of 2, it's simply telling me that the person who's evaluating this function plugged in 2 for x. It doesn't mean that I'm doing f times 2. So this is just our function notation, the function of 2. So if I plug into my equation here, that x is going to get replaced by 2. That's what this tells us. So if you see something that says like f of 7, it means they want you to plug in 7 for x. It's just a different way of telling you that information. So f of 2 equals, remember order of operations, we do multiplication first. So negative 4 times 2 is negative 8. Bring down that plus 7. So for this one, f of 2, negative 8 plus 7 is negative 1. So the solution to the function when x equals 2 would be negative 1. Now I'm going to do the same thing again, but this time I'm going to use negative 2. So again, I just plug it in. So I know that I'm checking this function for negative 2. So anywhere I see x, I have to plug in negative 2. All right, so negative 4 times negative 2 is positive 8 this time. Bring down that 7 we didn't use yet. So f of negative 2, 8 plus 7 is 15. So what we have here when they asked us to check for f of 2, the function of 2 would be negative 1. The function of negative 2 would be 15. For example 2, we have let f of t, or the function of t, be the outside temperature in degrees Fahrenheit, t hours after 6 a.m. So what we're going to do is explain the meaning for each one of these statements. So when I see f of 0, that means that we plugged in 0 for x, or in this case, time, right? T was time. So we plugged in 0 for time, which means it's 0 hours. T here, we plugged in 0, right? So it was 0 hours after 6 a.m. So at 6 a.m., because it's been 0 hours since then, at 6 a.m., the temperature is 58 degrees. So the temperature at 6 a.m. is 58 degrees. That's what that function notation means. So the function of 0 hours after 6 a.m. equals 58 degrees. For part B, we have f of 6 equals n. So we know that it's the temperature 6 hours after 6 a.m. So if we think about it, that's 7, 8, 9, 10, 11, 12 p.m., so 12 noon. So the temperature at noon, which we're going to remind ourselves is 6 hours later, is, and it says that it's equal to n. So not very informative for us, but it's n degrees and Fahrenheit. I should have labeled this one up here, Fahrenheit as well. All right, and then for part C, f of 3.5 is less than f of 9. So the temperature 3.5 hours after 6 a.m. is less than or colder than the temperature 9 hours after 6 a.m. So we think about that. The first one, 3.5 hours after 6 a.m. would be 9:30 a.m. And again, we're going to remind ourselves 3.5 hours after 6 a.m. And we know that it is less than, right? Because there's our less than symbol right there, less than or colder. So it's less than our temperature. And it said 9 hours after. All right, we know 6 hours after is noon. So then we have to go 3 more. 1 p.m., 2 p.m., 3 p.m. So the temperature at 3 p.m., which again, we're reminding ourselves was 9 hours after 6 a.m. So for those ones, we're just interpreting that function notation. What does it mean in relation to the problem that we've been given? All right, moving on to example 3. Example 3 says, solve for h of x equals 2/3 x minus 5. Find the value of x for which h of x equals -7. So if they're telling us that h of x equals -7, that means I have to, in my original function notation, replace h of x with -7. It's just like when they say x equals 5, we replace x with 5. So it's a similar situation here. So we're going to write down our equation, our function. So h of x equals 2/3 x minus 5. And since we know h of x equals -7, according to what they want us to double check, we're going to plug in -7 there. And then we're going to use our solving equation skills from previous lessons to figure out what this is going to be. So first thing I want to do is undo this addition here and add 5 to both sides. So that makes 0. We have 2/3 x equals -7 plus 5 is -2. 2/3 times x. We have to undo that multiplication by dividing. When we divide fractions, we keep change flip. So multiply both sides by 3/2. We're going to make that one a fraction. All right, so these fractions over here are cross-canceling each other. We're left with x. Give that guy some color. All right, x equals, well, I'm noticing here, these 2's will cross-cancel. So 3 times -1 is -3. So in order for h of x to equal -7, as I said, x would have to be -3. For example 4, it says, graph the function of x equals 2x plus 5. So what we have to do for this is we have to make a little table and figure out some points. So I'm going to suggest that, let's make our table right here. We're going to choose, I like to choose a few negatives, so I'll do -2, -1, 0, 1, and 2. Now, depending on the graph that you're given, sometimes those aren't always going to work out, but these are kind of the go-to sometimes that work out. So what we're doing is plugging each of them in to our function here. So we have 2 times -2 plus 5. Well, 2 times -2 is -4, plus 5 is +1. 2 times -1 plus 5. Well, 2 times -1 is -2, plus 5 is +3. 2 times 0 plus 5, well, that's 0 plus 5, which gives us 5. 2 times +1 plus 5, that's 2 plus 5, which is 7. And then we have 2 times 2 plus 5. So we have 2 times 2 is 4, plus 5 gives us 9. So we are going to take these points, because notice it's x and then y, so those are ordered pairs. We're going to take those points and we're going to put them on the graph. So on my graph here, I have -2, +1, -1, +3, 0, 5, 1, 7, and 2, 9. All right, example 5. The graph of G shows how far a helicopter is from its destination after taking off. The function f of x equals 350 minus 125x represents a second flight, where f of x is the number of miles the helicopter is from its destination after x hours. Which flight takes less time? So a couple things that we're going to look at. We have to make a table because we already have G on here. We just have to make the information for f of x. So they give us our equation here, our function, so we can make a table just like we did in example 4. So we have x, we have f of x. I'm going to choose, since we're talking about miles, doesn't make sense to do negative numbers this time because all miles would have to be positive. So I'm just going to do 0, 1, 2, and 3. So just like we had in example 4, we have to make sure that we're plugging these numbers into our function here. So we have 350 minus 125 times 0. So 350 minus 0 is 350. And then we have 350 minus 125 times 1. So 350 minus 125 is 225. 350 minus 125 times 2. Well, that's 350 minus 250, which gives us 100. And then if we did 3, we have 350 minus 125 times 3. So we have 350 minus 375, which would be -25. So that doesn't really help us out too much with that part of it. All right, so we're going to plot these points on our graph. So we have 0, 350, and then we have 1 and 225, so about halfway, there we go. We have 2 and 100, but then at 3, we would be down here underneath, right? So connect these here, kind of like that. And it says, which flight takes less time? So if we're looking at it, if we're talking about hours, it takes less time for flight B, that f of x, for this, because they get down to the ground before that function G does.